Hello, everybody. We'll let everybody come in from the waiting room and probably getting a few people logging on as we get started here. I would like to welcome everybody to tonight's workshop. It's the overview of the Model Battery Energy Storage System Law. And yeah, we're getting some more people signing in. It's good to see. My name is Nancy Bernstein. I am an energy circuit rider for ANCA, the Adirondack North Country Association. I'm also the Clean Energy Communities Coordinator for the North Country region. I'd like to encourage everyone to make sure that you're muted once you sign on, if you aren't automatically muted. And also, if you can get a chance, it would be really helpful if you could change your Zoom name, the name that appears on your little screen, your box, so that we know who you are. It helps us with taking attendance. I do my best to guess who you are based on your name of your iPhone or your iPad, but if you could change your name, that would be great. To do so, you just need to hover over the little, hover your mouse arrow over your picture or your name, and you'll see 3 dots in the upper right-hand corner. If you click on those dots, you'll have an option to rename. Click on that and you type in your full name and save it, and there you go. Your name will be changed. So that would be very helpful. Otherwise, another way to just say hello to each other is if you could put your name in the chat and include whichever town or village that you serve, then we can see who else is here. And just as a thank you to everyone for your service that you do provide for your community, because we know that it's really worthwhile work that isn't always appreciated fully. I mentioned a moment ago that I was the Clean Energy Communities Coordinator in the North Country, so I'd just like to give you a brief introduction to what the Clean Energy Communities Program is. It is a program of NYSERDA, the New York State Energy Research Development Authority, that provides opportunities for municipal leaders to improve their community, access grant funding, and earn recognition as clean energy leaders. With free coordinator support and guidance for implementing high-impact clean energy actions, municipalities have a clear path to building community-wide resiliency and economic opportunity. The program is based upon completing actions that provide benefits in and of themselves, such as converting your streetlights to LED, installing EV charging stations, or benchmarking energy usage in municipal buildings. Each municipality can customize its participation in the program to best fit their needs and resources, and to bring energy savings and economic opportunities to the entire community. For those of you in Jefferson, Lewis, and St. Lawrence counties, which I know many of you are, I'd like to introduce Shania Hull, is our newest Clean Energy Communities Coordinator. And I'd like to give Shania a chance just to say hello and introduce herself. So, are you there, Shania?
Yeah, I'm here. Hi, everybody. Nice to meet you. Unfortunately, I probably won't have much to contribute to today's discussion, but I'm here to learn and excited to work with all of you. And I'll put my contact information in the chat box.
Great, thank you, Shania. Shania is only on her second day in this role. She's from Watertown, and so she will be covering Jefferson, Lewis, and St. Lawrence counties, and will be a good resource. So you might like to write down her email address to get in touch with in the future. Let's see, what else? Again, I'd remind you to stay muted during the presentation. But if you have questions during the presentation, to add them to the chat, and they'll be addressed at the end of the program. And we will be providing the slide deck and a recording of this webinar afterwards. Continuing education certificates for planning and zoning board officials are issued by each county, so you'll be receiving them if you've attended any earlier sessions. It's the same routine. But other than that, I'd like to introduce tonight's presenter, Bill Oberkehr. He's from NYSERDA, and he will be speaking to us about battery energy storage systems. So thank you, Bill.
Thank you, Nancy, and thanks everyone for joining tonight. Please just bear with me while I get into slideshow mode. All right. All right, good evening, everyone. As Nancy said, my name is Bill Oberkehr. I'm a senior project manager on NYSERDA's Clean Energy Siting team. Going to deliver the presentation tonight about battery energy storage system model law. For folks who attended a few weeks ago, this will be a bit similar to the solar model law presentation that I delivered earlier in the month. Similarly, there is an energy storage model law template in the energy storage guidebook on the Clean Energy Siting website, which I will show you in a slide or two. And you can find all of that information pertaining to the law in our guidebook. In addition to that, since we are talking about energy storage, and as you will hopefully come to learn throughout this presentation, I do tend to beat it to death. Energy storage is very different from solar from a land use perspective. And there's one key reason for that. Energy storage requires very little space to store a lot of energy, whereas solar requires a vast amount of space to generate a modest amount of energy. So the land use implications from that are significant. So there's not as much in the way of considerations for zoning for energy storage. So as folks may be able to guess, a significant portion of the presentation tonight is going to revolve around the fire hazard that lithium-ion battery systems can present and what has been done to control that hazard. And really, a lot of this is just aimed at putting folks at ease a little bit and kind of demystifying the context of that risk and what has been done to address it, because there really, as you'll see throughout the presentation, there's really been a lot of work done by a lot of really qualified people to make sure that these systems are safe. And without further ado, let's go through our presentation. First, we're going to look at New York State goals, programs, and policy. Just to set up, why we're expecting to see energy storage technology proliferate throughout the state. And we're going to do a brief introduction to the technology itself, followed by the model law, and then a very abridged fire safety training. And then we should have time for Q&A at the end. So as I said, I would let you know a bit more about the guidebooks from NYSERDA. Here they are. You can look over there to the right. There are 4 principal guidebooks that the Clean Energy Siting team at NYSERDA is responsible for. We have the Solar Guidebook, the Wind Energy Guidebook, the Energy Storage System Guidebook, and the newest edition from December 2021 is the Clean Energy in Your Comprehensive Plan Guidebook. Tonight, obviously, we're going to be focusing on the battery energy storage system guidebook. All of these guidebooks and all of their chapters, all that great content is available through the link at the bottom left, nyserda.ny.gov/siting. And if folks, have any questions that are better suited for me, you can reach out to me or my team, and I'll show you that email address when we do questions at the end. All right, so to ground, what we're doing here and why we expect to see this technology proliferate, we have to take a look at New York State policy. Our leading climate legislation is the Climate Leadership and Community Protection Act, otherwise known as the Climate Act, otherwise known as the CLCPA. I will use all 3 of those terms interchangeably, or I might. Just know that they all mean the same thing. I'm not referencing 3 different pieces of legislation here. Here you can see the core tenets of the Climate Act, 70% renewable electricity by 2030 with 100% emissions-free grid by 2040. And then we've got technology-specific goals of 10,000 megawatts of distributed solar by 2025, 9,000 megawatts of offshore wind by 2035, and then 1.5 gigawatts of energy storage by 2025 as an interim goal of 3 gigawatts by 2030. 1,000 megawatts is 1 gigawatt, so we can also use those terms interchangeably if folks aren't aware of that. So we've got 10 gigawatts distributed solar, 9 gigawatts offshore wind, and 3 gigawatts of energy storage. That energy storage goal, if folks paid attention or caught the last state of the state, is likely to be doubled, which we'll see in a slide or two. And lastly, on this slide, I want to just call everyone's attention to the graph at the bottom. This is what's known as our energy mix. Going back to the 80s and even earlier than that, our energy has never come from one source. And as you can see here, the trends over time where, as coal plants start to close in the aughts and natural gas takes on a big part of our generation, you see that happening. And then the nuclear line also, you can see this graph terminates in 2017. That is before Indian Point starts to shutter. So what has almost certainly happened in between now and 2017, the last 5 years, is that a greater share of this chart is green for renewables and a smaller share is orange-brown for nuclear. So this is just to give folks an idea of, where are we getting our electricity as it stands for the past, generation or so. Large-scale renewables. So every year since 2017, NYSERDA has issued a large-scale renewables solicitation. That is a open RFP for projects or for developers to bid in a price to have NYSERDA enter a contract to buy the RECs, renewable energy certificates, generated by the system for its life. What a renewable energy certificate is the legal claim to the environmental attributes of the energy generated by clean energy assets. So that legal claim has value, and NYSERDA purchases that legal claim through this program. That is not to say that when these projects are awarded through NYSERDA, they are permitted. NYSERDA is not a permitting authority. Most of the projects in the large-scale renewable solicitation going forward will go through the Office of Renewable Energy Siting, which was established in 2020. But our most recent slate of awarded projects in 2021 were 22 solar projects with 6, including co-located energy storage. I believe the previous solicitation was 3 energy storage projects co-located with the solar. So we've about doubled, which is probably a pretty good indicator of what we expect to see happen to storage going forward. So that's going to be, I missed the important part. So this is for projects that are 7.5 megawatts and above. That's what we would consider large scale. Although the way the economics work out, you're typically not going to see projects below 20 megawatts. There's kind of this dead space in a lot of ways between 7.5 megawatts and 20 megawatts. And that has to do with the way that economies of scale interact with the wholesale market versus the distributed market for electric generation. So we have the energy storage initiatives for energy storage projects up to 7.5 megawatts. So this is another NYSERDA program. As you can see again, that 3,000 megawatt goal is likely to be increased twofold to 6,000 megawatts by 2030 for the governor's state of the state. The way that will be finalized is through the energy storage roadmap, which NYSERDA will release by the end of the year is the scheduled timeline for now. And that has to go through Department of Public Service to be approved, at which point, should it be approved, then our official goal is 6,000 megawatts. So that's a little insight into the process there. The two main components of the energy storage initiative or NYSERDA are incentives and technical assistance, both of which are available through my team and through the energy storage team here at NYSERDA. So that's our policy framework, a little bit of background on why we're here and why we expect to see energy storage. So let's talk about what energy storage is. Energy storage is basically creating potential energy. So it's the conversion of kinetic, electrical, or other forms of energy to that potential energy. There are various different types of stored energy, as we can see a little bit better here. We have pumped hydroelectric, mechanical, thermal, chemical and electrochemical. All of these have different applications. All of these have different pros and cons. For the purposes of tonight's presentation, we're going to focus on electrochemical exclusively. So everything that I will say tonight pertains only to electrochemical batteries. And even within electrochemical, we're focusing even further, drilling down a little more to lithium ion specifically. So that's really where most of our information tonight is going to pertain. And then we'll talk a little bit about flow batteries too, I believe even on the next slide or two. So this is the basic makeup of an energy storage system. Electrochemical, that is. All electrochemical energy storage systems are basically going to consist of these things, although what we're looking at here is a lithium ion system. So we've got in the basic building blocks, the cells, those are those little AA looking things. When we have a bunch of cells wired together, we have a module. When we have a bunch of modules wired together, we have a rack or a unit. Those two terms can also be used interchangeably. And those are the basic components. Would like folks to pay attention to these building blocks here, commit those to memory to the extent possible, because they will be relevant when we talk later about fire testing for energy storage systems. All right, so this is just a quick chart to sum up how these different electrochemical energy storage technologies compare to each other. I'm going to highlight a few things here. First, round trip efficiency, what that means is the amount of energy that's charged that can be discharged also. So between 85 and 95% of the energy that's used to charge a lithium ion battery is sent back, is able to be discharged. So very high round trip efficiency for lithium ion as compared to other electrochemical energy storage technologies. The duration is the amount of time over which that battery discharges. This is the 1 weak spot, if in my opinion, of lithium ion. If you see here, we've got 15 minutes to 4 hours of discharge time. Our grid peaks are not guaranteed to be kept to 15 minutes to 4 hours. So what that means is you would either need a lot of extra pieces of equipment that discharge over 4 hours, or you would need fewer pieces of equipment with a longer discharge time, a longer duration. And if you look to the left at flow batteries, you can see that they're much better in terms of duration. So flow batteries can discharge over 12 hours, which is probably a bit closer to what we would expect to see from a grid peak. There are federal R&D efforts as well as state R&D efforts to get at what's called long duration lithium ion storage. So what that effort essentially is to get that 4 hour mark up closer to 12 hours where flow batteries are, so that we see lithium ion batteries discharging over longer periods of time to help us meet grid peaks. Time to build is pretty similar across the board. Operating costs are lower for lithium ion than for other technologies. Huge reason why we see it out in front of these other technologies in terms of adoption. The other big reason, the space required for lithium ion batteries is typically much smaller than the space required by other chemistries. If you remember, I said at the very beginning, I'm going to say this at least 3 more times, so please bear with me. From a land use perspective in particular, you can see here lithium ion is going to require a small space. And then in that small space, you can store a really significant amount of electricity. With solar, you need a very large space to generate a modest amount of electricity, which from a land use perspective, that has huge implications. And then down to cycle life, you see we're pretty similar across the board, with lead acid lagging very far behind the rest. And then another reason we see more lithium ion than other types is because we are at a commercial level of technological maturity with lithium ion products, whereas the longer duration flow batteries have less round trip efficiency and are not quite as mature. And lead acid, though it is a mature technology, has a bunch of other kind of strikes against it here with the high operating cost, the low cycle life, the relatively low efficiency, the large space required. So this is really why we see lithium ion at the front of the pack for proliferation throughout the state as an energy storage technology. Not because it's the only one, but because especially over developments in recent years, it is the most commercially viable. To give folks a feel of what lithium ion batteries look like, we've got the 3 typical classifications that you will see. Residential and commercial are both behind the meter. What behind the meter means is that they service a local load. What front of the meter means is that the energy goes directly into the grid without servicing a customer first. So for behind the meter, those servicing a local load, we have residential. The local load that they serve is the house. And commercial energy storage installations will serve a commercial customer, typically for the purpose of demand reduction or peak shaving. Essentially just 2 different ways to lower your energy bill. And then for these utility scale systems, they are, as I said, discharging energy directly to the grid. They're not servicing a local load. And these are the big, shipping container looking energy storage systems. And this is really what we're mostly worried about from a land use and zoning perspective. It's these big guys. For the residential and commercial, most of what you would need to consider is captured by the fire code and the residential code. So for zoning, we're very much targeting these utility scale installations and maybe some commercial, but certainly less of a focus there. Got some more components of these systems. In addition to cells, modules, and racks, we have the battery management system. That's the eyes and the ears and the brain of the system. It's going to monitor each individual cell within the system. It has the ability to send an alarm if there's an irregularity or potential issue within the cell. And in addition to sounding an alarm, certain battery management systems are also capable of isolating the problem area of the system. And in order to keep any issues from spreading. So not only is the battery management system typically capable of sounding the alarm, it is also typical of reacting to catastrophic conditions or potentially catastrophic conditions. Land use considerations. I'm going to spend a majority of this time differentiating energy storage from wind and solar. But there are land use considerations for all of the technologies, and some of them are the same. We need to determine appropriate zones. We need to do environmental impact study, typically through the State Environmental Quality Review or SECRET. Bulk and area standards decommissioning is going to come up for all of them, although energy storage has decommissioning plan required by the fire code. So it's a bit less of an issue for local legislation because it's already covered by the state legislation and the state codes. And finally, taxation. And one thing to note, we have solar and wind both have these visual and aesthetic impacts. Energy storage really does not. And one more time, the reason that is because energy storage can store a large amount of energy in a small space. So when you don't need acres and acres and acres to store a megawatt, then you reduce the visual and aesthetic impacts because you're able to use a lot less land to be able to store the same amount of energy. Energy storage is not inherently renewable, nor is it energy generation. It is storage, so it needs to be charged. Batteries are agnostic to what they're being charged from unless they're specifically paired, as in the large-scale renewable solicitation, with renewable generation. So the top you see the renewable sources, the bottom you see the grid, both charging the battery. As we get past the battery here, this is a good example of front of the meter versus behind the meter. Behind the meter would be this top arrow that's going to the house. That means that that battery is discharging to the local load in the house first, and any excess is then going out to the grid. Versus front of the meter we have down here where the energy is just going straight to the grid without servicing a local load first. This is an intimidating image that we will break down over the next few slides. But another way that energy storage is very, very different from solar. Solar is more or less a set it and forget it technology. It just sits there and generates electricity when the sun is out. Energy storage is far more complex than that. It can provide up to 13 services to 3 different stakeholder groups. You see the stakeholder groups in the outer circle there. Customer services, those are behind the meter, as I said, so typically a home or business. Utility services, that's going to be your local distribution utility. And finally, grid services, that's in New York, the New York State Independent System Operator, or NYSERDA. So that's our transmission infrastructure. Primary uses for customer services are backup power. If you have just solar without a battery and the power goes down, you are not going to have power because your inverter will sense that there's a power outage and shut off production. With energy storage paired to that solar, you will be able to have power in most cases during a broader power outage because energy storage technology can provide the capability to island from the grid. Another use is increased PV self-consumption. So we don't have enough space on the roof to zero out our load in the house. We can add energy storage technology to cover that gap and get to 100% offset if needed. And then finally, demand charge reduction and time of use bill management, both typically for commercial enterprises, essentially just ways to charge while energy is cheap and discharge while it is expensive to be able to save money. That's an oversimplification, but for our purposes, I think that's probably a good way to think about it. And those are all the behind the meter use cases. This is the utility service. So this is your local utility. I believe we're in national grid territory. So this would be national grid. So distribution and transmission deferral. Energy storage can give the utility the ability to defer those costly upgrades because they can put storage in instead of building new infrastructure. Energy storage can also provide congestion relief by mitigating congestion in areas with lots of generation or inadequate transmission capacity. The reason energy storage can do this is because energy storage can pull energy off the grid and push energy onto the grid. Depends on what the grid needs at the time. Energy storage is nimble enough to adapt to the needs of the grid as a technology, which is another reason that we see this technology proliferating so quickly because it is very, very useful. And then finally, for resource adequacy, the more stored energy there is connected to the grid, the more energy we have to keep the lights on. And finally, this is probably the least important for our purposes, but I'll go through them anyway. These are the transmission use cases for energy storage. We've got energy arbitrage, which is charging when electricity costs are low and discharging when they're high. Pretty much the same principle as load shifting or peak shaving for a commercial application. This is just done on energy arbitrage is just done on a much larger scale. Spin, no spin reserves will dispatch energy as needed to ensure the grid supply equals demands. That's one of the instances where it is very handy to be able to push energy onto the grid and pull energy off. Frequency regulation. We can quickly ensure generators are synchronized for grid stability. Voltage support can provide or absorb voltage as needed for grid stability. Those last two are generally referred to as ancillary services. But you see the last three all hinge on the technology's ability to push energy onto the grid or pull it off. Gas-fired peaker plants can't do that. Solar can't do that. Wind can't do that. So we really have a potentially valuable and really game-changing technology here from a grid operations perspective. Another use case that I'm not going to belabor too much is we can use energy storage to replace gas peaker plants. There are a variety of benefits to doing that. As summarized here by the range utilization, dispatch time, and standby. We'll go to utilization. Peaker plants are only fired when the grid is at its peak. And as you could probably surmise, in order for the grid to be at its peak, that means it only happens once, right? Because it's the highest point. And there can only be one, maybe there's a tie. So really, a lot of these plants are getting turned on maybe a few times a year. And other than that, they have no function. They just sit there and collect money and frankly ratchet up all of our energy bills. Energy storage, on the other hand, can be a peaker when it needs to be, but other times it can do other things. Because it is so versatile as a technology and there are 13 different use cases, it doesn't have to sit there dormant and wait for the grid peak. It just, we have some idea of when those grid peaks are going to be. It needs to have that energy on hand for when the grid is likely to peak. But for the rest of the year, especially in off seasons, we typically have a summer peak, at least in most of the state for now. So during the winter, that energy storage technology is not just sitting idle for the whole season. It's able to contribute when it's not in use for peaking purposes. Dispatch time. So as I said, these peakers only go into use when the grid is at its peak. When the grid is at its peak, that means we are likely close or on the verge of brownout or a blackout. So the difference between minutes and seconds is crucial. Energy storage being more nimble than a gas peaker, which needs to be fired up, versus energy storage can just discharge pretty much instantly. It's a much more versatile technology. And then finally, when it's in standby mode, so all that time that it's not in use, gas peakers, as I said, cost a lot of money for upkeep and through our electricity bills, and they will still emit, whereas energy storage will not have any emissions from the storage itself. Of course, the energy that the storage system is using to charge might have emissions associated with that, but those are not coming from the storage. That's coming from the initial generation, and no cost while energy storage is sitting idle. We're taking a look at how much energy storage we have in New York so far. These numbers are dated in April because that's when the Department of Public Service releases their report. And those are typically the best numbers. So right now what we're looking at is about 1,200 megawatts contracted and under development, and over 100 commercial bulk projects. So 1,200 megawatts and 100 projects. Not that that's 100% of it, but we've got some big projects in there. Is really what we're trying to say. And now let's get into the model law. We're going to do a little bit on the model permit, a little bit on the model law. Again, both of those resources are available in the Battery Energy Storage System Guidebook for Local Government, which is available via NYSERDA.ny.gov/citing. So you can find all of this information on our website anytime you need it. Don't feel the need to take all the notes or memorize it right now. So we've got 4 chapters in the Energy Storage Guidebook as compared to, I think, 12 in the Solar Guidebook. We're going to go through chapters 1 and 2 today, the model law and the model permit. In addition to those, we have an energy storage inspection checklist. It's designed for electrical inspectors. It is a Word document, so you can tailor that at the local level to really meet your needs. And then finally, chapter 4, what we did was pull all of the information, the sections that are relevant to energy storage technology from the fire code, the building code, the existing building code, and the residential code, and we put them all in one place. That is for reference only. If you just need to look something up quickly without sifting through a 1,000-page document that is the fire code, you can pull that up, but always best to double check and cross-reference with the actual fire code once you've found what you need. We've got different ways of permitting energy storage systems depending on whether or not they are paired with renewable generation and their size. If an energy storage system is paired with a renewable generator of less than 25 megawatts, that is going to be permitted at the local level through the State Environmental Quality Review or seeker and any municipal and county requirements. If, however, the energy storage is paired with a renewable generator over 25 megawatts, that's going to be permitted at the state level through the Office of Renewable Energy Siting and the Title 94C process. It is a common misconception that the Title 94C process will just disregard local regulations and local comprehensive plans. That is absolutely not true. The state process does take heed local requirements. So very good to have those on the books. It's just one of the ways that you can, make sure that the community of your character is being taken into consideration at the state level as well, should you have projects of that size enter your community. Finally, standalone systems, regardless of their size. So that's energy storage that's not paired with any generation directly. It's just charging from the grid. That's always going to be permitted at the local level through state environmental quality review and municipal and county requirements. All right. So this is our overview of our zoning law. These are the different sections. I'm going to go through this pretty quickly, just because, as I said, this is all available in the guidebook. First is the authority. Like in the solar model law, we are starting out with the authority, and it's the same thing. Basically, what NYSERDA has done here is just comb through the laws and pulled the relevant citations that you would need. So you have to select whether you're a town, a village, a city, or using municipal home rule. Where does your authority lie to have zoning in the first place? So that's all this is really saying. And anytime you see this gray highlighted and bracketed text throughout the law, that means action is required on your part as the municipality to fill in the correct information. Beyond that, both the solar and the model storage law are sort of infinitely tailorable. So you could just go through and look for the gray highlighted sections and fill them out and pass that. That would be perfectly fine. That would be perfectly legal. Or you can go through it with a fine-tooth comb and change more provisions of the law than not. Not that I would recommend doing that, but you are free to, and that is also fine. So really versatile tool that we have here in both the solar law and the energy storage law, as all of those characteristics apply to both. First part, definitions. We break energy storage systems into two tiers. The cutoff for those tiers is 600 kilowatt hours of capacity. The reason for that cutoff is to harmonize with the fire code. We will see the 600 kilowatt hour capacity threshold come up several times. So I get asked quite frequently, why did we set that capacity threshold there? The reason for that is to harmonize with the fire code. We want the requirements to align, or our advice is to have the requirements aligned to the extent possible and to the extent that makes sense. And we at NYSERDA thought it was made a lot of sense to have the same threshold as the fire code does here. So less than or equal to 600 kilowatt hours, we're going to have tier 1, which means easier requirements. We're not as concerned about those just because they pose less of an issue from a land use perspective. And then we're going to get a little more scrutiny on the projects that are greater than 600 kilowatt hours. So these are all tier 1 just to give you a feel for the range of sizes. We've got a couple residential installations on the outsides here, a couple commercial ones on the insides. This one is the largest here. It looks like it's in a house from the 70s, judging by the wood paneling on the wall. But that, to give you, a frame of reference for the size, it's probably going to be about the size of maybe 4 refrigerators. So that's about how big that is. And the other ones, as you can see, are pretty small. And these are tier 2. That's when we start to get into things that look like shipping containers. And again, that's where we start to really focus our land use regulations, because as you can see, these are much more significant from a land use perspective than, something that's just mounted on the side of the wall of a home. So here are the permitting requirements that NYSERDA is suggesting through the model law for the 2 tiers. For tier 1, NYSERDA is suggesting that you adopt the battery energy storage system permit and the inspection checklist to be able to permit those systems through your building department, and then strongly advising as a state law to apply the fire code as it applies. And then for those tier 2 energy storage systems that are over 600 kilowatt hours, that's when we're going to get into a special use permit, site plan review, and then obviously the fire code will still apply. So you see the more traditional land use regulation tools coming out for the tier 2 systems, as I've said. This is what the energy storage model permit looks like. If folks are familiar with the New York State Unified Solar Permit, and if you attended the last course that Chris Doty did, which went on at length about the solar permit, this is the same thing in principle. It is just a permit for storage instead of solar, but same steps to pass it, same prompts to fill in. What's your permitting fee? How would you like to be paid? Things like that. But this is where we get different from the solar permit. So all of the substantive information contained herein applies to energy storage. And really, this permit should function as a cover sheet for a permit application. We don't necessarily just want folks handing you this piece of paper. This should, have accompanying documents and plans, some of which are laid out here. And again, this is also infinitely tailorable. So you can add things that you would like to see. And to that end, I believe the Energy Storage Guidebook has a Word and a PDF version of the model permit. So you can go in there without having to do too much work in the Word version to add in any requirements. Though we don't suggest that you take any out, particularly things like this requirement to have constructing documents signed and stamped by a registered architect or professional engineer. That is state law. So another handy thing about the energy storage system permit and the solar permit is that they will keep you in compliance with state law, without really having to do all of that digging yourself. So now that's what we're NYSERDA suggesting for tier 1, and we're suggesting that folks allow tier 1 systems in all zoning districts, because as I have said almost ad nauseum already halfway through the presentation, the small energy storage systems are not really going to have much of a land use implication. Most of the issues that can arise with those, or most of the regulations that are around those, are handled in the fire code and the residential code. When we get into tier 2 systems, we're looking at something that's a little bit more impactful from a land use perspective. So we've got a more scrutinous process of approval here. We're going to choose which zoning districts to permit systems. So we're not just going to blanket tier 2. We're not going to just say that tier 2 systems can go in all zoning districts like we will for tier 1. And then we've got our site plan review process here. And this follows the requirements that are common or I think mandated for any other type of development. And then we've got some requirements for approval over here. a lot of these are similar to solar, but even though the overall categories are similar to solar, the substantive requirements are not similar to solar. Decommissioning is the one that we really like to hit here because I find it's often the issue of greatest concern to folks. The decommissioning plan is required for energy storage systems by the fire code. So that's great. What is not required by the fire code is a decommissioning fund. And what that is a security in the event that the developer or the owner of the system fails to decommission the system and restore the site. The municipality will have that security to be able to cover those costs. I would argue that, again, because with solar, we are dealing with acres and acres and acres. So a fund like this is really necessary. With energy storage systems, you're dealing with, maybe 10,000 square feet of development or somewhere in that ballpark. I've heard a lot of folks argue that the decommissioning fund is a much less necessary for storage than it is for solar. As it is right now, our model law still recommends that you have one. That's what this slide is addressing. So we need the decommissioning plan to tell us the anticipated life of the system, the costs associated with decommissioning the system and restoring the site, how those estimated costs were determined, and a method of ensuring available funds for decommissioning and restoration. So that's the decommissioning fund that you see over there on the side. And then we want to keep that decommissioning cost current, protected against inflation and other things, to make sure it still accurately reflects the cost to decommission the system and restore the site. And then we've got the decommissioning fund, some details there. That will be continuously maintained in a fund or a bond payable to the city, town, or village for the removal of the system. The form and amount to be approved and determined by the municipality could consist of a letter of credit. And finally, most importantly, all costs of the financial security are borne by the applicant or the project developer. So this is the NYSERDA recommendation as it stands. Just a little bit of color, and again, my opinion, this is probably much less important for storage than it is for solar, but still probably good to have to protect the municipality's interests. We've got some other permitting requirements here for tier 2. As you can see, it's not going to be as simple as just filling out that model permit and supplying some additional documents. We've got a lot more that we want to see from these tier 2 systems. I want to really hit number 9 and number 13. That's why they're emboldened. We've got a fire safety compliance plan, an emergency operations plan. Those are both going to be required by code, but good to harmonize your local requirements with the code. So a good idea to include them in your zoning law as well. And a lot of other aspects here are going to be required by code as well. Typically the fire code, such as a commissioning plan and operations and maintenance plan. These are the requirements. Not going to read them all, but really want folks to take away that we're looking at fire and emergency here. And we are also creating much more stringent requirements for these tier 2 systems that are over 600 kilowatt hours than for the smaller tier 1 systems. All right, so as promised, the energy storage model law section of the presentation is pretty brief. It's really all there is to it. The main takeaway is, as planning and zoning folks, we're not that worried about systems under 600 kilowatt hours in capacity because we're going to let the fire code and the residential code do their jobs. And then we've got some more stringent land use requirements for systems over 600 kilowatt hours. Onto fire safety, because typically when I do these energy storage presentations, that's what folks are the most curious about and have the most concerns about. So really like to take the time to address it. So this is a history of codes and standards that apply specifically to energy storage systems. Can we do reactions? No, that's probably too much. Would just like to get a feel for how familiar folks are with codes. But it seems like that might be tough to accomplish, so I'm going to treat it like folks don't know that much. So please bear with me if you're a codes whiz. So we've got the main players listed over here on the right. This is a good sampling of what we call the fire safety industry, or the electrical safety industry. UL is Underwriters Laboratory. ICC is the International Code Council. They draft the international codes. The international codes then serve as the basis for the New York State codes for the Uniform Code. So that's how that works. And then the National Fire Protection Association, which is probably the lead in fire safety in the country. So these are our main regulators that are designing the codes and standards that we use to regulate energy storage systems. So some real heavy hitters here. So back in 2016, UL publishes the first edition of UL 9540, which is a listing standard for energy storage systems. And then a year later in 2017, UL publishes the first edition of UL 9540A, which is the test method to evaluate system safety and inform installations. Apologies in advance. I am about to beat this to death. Because as folks may be able to imagine, UL 9540 and UL 9540A get confused with each other a lot. They're not the same thing. They're not even the same type of thing. So I'm going to hit this pretty hard because my goal for this particular presentation is to have no one leave it without understanding the difference between UL 9540 and UL 9540A. If you already understand that difference well, maybe come back in 5 minutes, just kidding. So UL 9540 is a listing standard. So when you see UL on electrical equipment, typically on a plug, you'll find it. I'm looking for something with a UL mark within my grasp, and I don't have one to show folks what that looks like. But if you see a UL mark on a product, typically you'll find it on the plug, as I said. That means that is certified by UL. That means that UL has tested this product. This product has passed all of those tests, and UL is essentially saying that this is safe. So what UL 9540 means is that every component of the system has been tested with each other. So that means the cell and the inverter and the fire suppression equipment and the cabinet have all been tested together as one unified system, even though they're different components. And even though all of those different components have their own UL listings, what UL 9540 says that all of those components work together. So if I have a 9540 system, and then due to supply chain issues, I can't get a hold of the inverter that I use for that 9540 system, so I try to swap it out with a similar capacity inverter. By doing that, I will invalidate that 9540 listing. Once I switch that inverter out, I'm not 9540 listed anymore because, as I said, the 9540 listing establishes that all of the components of the system work safely together. So if you replace one element of that, obviously you're going to void that listing. So that's like a step, right? Like a pass-fail certificate of approval. You got it once you pass the test. And that's UL 9540. Now we're going to move on to UL 9540A. UL 9540A is a test method. And what that test method is Essentially, a bunch of folks in a lab will intentionally abuse a battery until it goes into what's called thermal runaway. And then they'll observe what happens when the battery enters a failure mode, and they'll record that. So we've got some guys who are, beating up a battery because they want to see what gases come out of it, how long it takes to go into thermal runaway, how does that thermal runaway spread throughout the system, all of these things, and then they're going to record those. That report then, the 9540A report, is used by local code officials to make siting decisions about the energy storage system. So what we see written into the fire code over and over again is large-scale fire testing, which is synonymous with UL 9540A. Large-scale fire testing and UL 9540A mean the same thing. What we see over and over again in the fire code is this exception, unless large-scale fire testing says otherwise, basically. So what that means is you, the code official or the fire marshal or whoever is evaluating for fire code compliance, is looking at this 9540A report that documents how this system behaves in the event of a catastrophe, and they're making the siting decisions based on that. So UL 9540 is a listing standard. That's a stamp. That means that everything in the system works together. UL 9540A is a test. It yields a packet of data for interpretation. It's not a stamp. It's not a credential. It's not a pass-fail test. It gives you a packet of data that you then need to interpret. So that's the difference. Again, UL 9540 is a stamp saying that all of the components of the system work safely together. UL 9540A is a report that tells you what happens when you abuse the system and it enters into failure mode. Very important distinction. Very few people know it. So I tried to really spend some time on that. So those are, within the last, 6 years, UL is looking at these systems a lot more closely than they had previously. And then in 2018, we have the International Code Council coming on board, at which point they introduce a chapter to the International Fire Code on energy storage systems. So that at that point, because it's between code cycles are 3 years. So this is between code cycles that the International Fire Code addresses energy storage systems in the way that they need to be addressed. So what the International Code Council does in 2019 is issues a temporary energy storage system supplement to the code. So basically, immediately when there was a need for this type of regulation, the International Code Council very quickly put those regulations together and turned them out, and they're still pretty much what we're using to this day. In 2019, the NFPA releases NFPA 855. So that is the energy storage standard for the National Fire Protection Association, rather. That is the basis of the new International Code Council section on energy storage. That's NFPA 855 informs our fire code and our residential code. So if you look at the two side by side, if you pull up chapter 1206 of the New York State Fire Code, which is the chapter on energy storage systems, and NFPA 855, and you read them side by side, it's almost the same document. New York is the first to adopt these regulations. New York adopted those regulations when they were still in draft form. Fortunately, not much change between the draft and the finalization. So New York adopts these in May of 2020. And then California is the next state to adopt, which doesn't adopt them until July of 2021. So for energy storage safety, New York has been way, way ahead of the curve. since the inception of energy storage safety considerations. This work in 2016 and 2017 is a lot of that with UL 9540 and UL 9540A. A lot of that comes directly out of the Underwriters Laboratory working with FDNY, the Fire Department of the City of New York. That's really where all of this, or a lot of this safety concern originates. So UL is working with FDNY to develop these standards. And then as a result of that, it's not terribly surprising that New York is really leading with adopting the most up-to-date, the most comprehensive regulations for energy storage technology, because New York is also at the forefront of kind of the creation of those. So really hoping that alleviates some of the pressure for local land use officials to, I've come across so many folks who think that if they, through their zoning, don't completely mitigate the fire hazard associated with energy storage, then no one's going to do it. And I hope understanding this alleviates that concern if you have it. People whose jobs 100% of the time are to deal with electrical and fire safety have looked at this, have come up with multiple iterations of safety standards and safety tests and safety documents. All of that work has been done for you before you ever see a project application. All of that work is mandated in New York State law. So, we're really in good hands here in New York. Is what all of that was building to. And I think, folks can't tell, I think this is actually the most important slide of this whole training. Just because it really does a great job of showing that, a lot of very capable, talented, specialized folks have been looking at this technology and vetting it and making sure that we mitigate those fire hazard risks that folks do tend to hear about. All right. This is thermal runaway. So that's what I was talking about. That's the purpose of the 9540A test, is to send the battery into thermal runaway. As you can see with number 1 there. Oh, let me start by explaining what thermal runaway is. Remember, we have the cells, the modules, the racks. Thermal runaway is when a cell starts to rise in heat exponentially. Once that process begins, it cannot be stopped. So we're not trying to stop thermal runaway anymore. We're trying to make sure that it doesn't spread. That's typically how firefighting works for energy storage systems. Once something is on fire, we're not worried about it anymore. It's not like it can be used again. We're just trying to contain that event. So it's a containment thing. Typically, the way that battery cells enter thermal runaway is through some form of abuse. You will not see thermal runaway and the normal charging and discharging of batteries. Then we'll see some off-gassing, probably some smoke, though not always. Fire will then come next, and then we have the concern about the fire propagating to other cells. Again, really looking at containment once we have entered thermal runaway, but there are things we can do to prevent it. Yeah, I'm going to go to this slide first. These are all of the different measures. So we've got our prevention over here. Start with good cell quality, good battery management system that can isolate cells and cool them down if needed, off-gas detection. And then once we've entered thermal runaway, which happens right here, there are a number of things we can do to contain it. And they're listed over here, good fire suppression, cooling and heat transfer plates, and a non-propagation design in the system. So these are all of the things that we can do to address, the somewhat rare instance of an energy storage system catching fire or going into thermal runaway. Here is what thermal runaway and propagation looks like in a very simplified form. So we've got one cell is overheating. That cell enters thermal runaway, which is an exponential rise in heat. So what happens is that cell is heating up neighboring cells, and then those cells are heating up neighboring cells. What a lot of battery management systems are able to do these days is, one, send out an alarm that this is happening, and two, actually respond. So we have battery management systems and fire suppression equipment that can do this. That can start to cool these cells and prevent propagation without human involvement. That will just, install through the brain of the system. And then we have all of these other measures as well. There's really a lot of controls here to really make sure that the worst does not happen with this technology. Saying that also to put folks' minds hopefully at rest a little bit in terms of the pressure of feeling like you need to mitigate this fire hazard through your zoning. There's really a lot of stuff done on the technical side, on the energy or on the safety industry side, on the code side. A lot of folks have put a lot of things in place to be able to manage that fire hazard. Here we are back in 9540A. This is also called large-scale fire testing. In the fire code, you will see it primarily referred to as large-scale fire testing. Anytime you see the words large-scale fire testing in relation to energy storage, we are talking about UL 9540A testing. We can use those terms interchangeably. The UL 9540A test, as you can see here in the second bullet, is performed at multiple levels. So remember at the beginning, I told you to keep in mind the cell, the module, the unit, all that great stuff. I did that for a reason. There is a different test at the cell level. So there's a 9540A for the cell, 9540A for the module, 9540A for the unit, and then an installation level 9540A test as well. So we have nationally recognized testing laboratories testing these systems at every level. I guess level is the right word there, to see what happens in the event of thermal runaway. And then those test results will inform system design and installation requirements. As I said, chief among them are fire mitigation and protection requirements, ventilation requirements, and then incident response as well. Fire code. So in 2019, as I said, the International Code Council released the Energy Storage System Supplement. Remember how I said these rules came out between code cycles. So the International Code Council releases the supplement to carry us over to the new code cycle. And then in 2020, New York adopts the new code that includes regulations for energy storage systems in the residential code, the building code, and the fire code. I feel like most folks might know this, but for those who don't, the uniform codes are applicable as state law without the need for local adoption. So the way to exercise your home rule power in relation to the uniform code, you can only use your home rule power to make the code more stringent. You cannot use home rule power to relax the code. So in essence, the uniform codes, the New York State uniform codes, are serving as a baseline for requirements for these technologies throughout New York State. All this with the exception of New York City, which has its own fire code, its own building code, and all of that great stuff. Anywhere else you go in the state, this 2020 Fire Code of New York State is what will apply right now. Before going into the fire code, let's go to the residential code. The residential code has a very small purview as it relates to energy storage systems. We've got size, location, and separation requirements. So we're maxed out at 20 kilowatt hours per unit. To put that in context, if folks have seen a Tesla Powerwall, which is this on the bottom, that's 13.7 kilowatt hours. So well below the threshold, and that is one unit. So we've got a 20 kilowatt hour unit max. We're only going to allow residential installations on attached or detached garages, exterior walls, and within utility closets and storage and utility spaces. By code, those are the only places in a home that energy storage systems are allowed to go. Although utility closets and storage and utility spaces are ill-defined, and they can really be a broad swath of places, but those are really the places that we are allowed to have energy storage. So any application needs to make a good solid argument as to how the site for the system is one of those spaces. So we've got a 20 kilowatt hour per unit limit, but we can go up to 40 or 80 kilowatt hours in aggregate. So either 2 or 4 units, up to 2 or 4 units, depending on the location. So I think you can go up to 80 on exterior walls and detached garages, and you're limited to 40 in utility closets and attached garages, is how that works. And then we've got separation, a minimum separation of 3 feet from other units, as well as doors and windows. And then we've got fire resistance rating requirements in the residential code as well for walls and ceilings of rooms and areas containing energy storage systems. And right down here, we see certain requirements may be modified by the AHJ based on large scale fire testing, which is the 9540A test once again. So as you can see, this bottom picture, this Tesla to this window, it doesn't look like 3 feet. And maybe that's an issue with the image or the angle or whatever. But let's just say for the sake of argument that that is not 3 feet. But here it says we need to have a minimum separation of 3 feet from other units, as well as doors and windows. So the way that that becomes possible, the way that this can be a code compliant installation is but through this requirement. So the code default says 3 feet from doors and windows, but we got those 9540A test results back, and the 9540A test results say that we can go within 18 inches. So the code has it built in so that 18 inches is your new requirement now, and you could disregard that 3 foot separation requirement. So that's what I keep saying by, the results of the 9540A test will actually affect the code and how the code is interpreted. That's what I mean. The results from that test can justify a smaller separation distances and other things, as we'll see in additional slides. But that is a good practical example of how that could work. For this slide, remember how I said the difference between tier 1 and tier 2 systems is set at 600 kilowatt hours because that number keeps coming up in the code, and we made that threshold in our model law so that we could harmonize with the code. This is where we're going to learn about that. As you can see from the top here, hazard mitigation analysis required for systems greater than 600 kilowatt hours. Bottom bullet here, large scale fire testing or the UL 9540A test required for systems at greater than 600 kilowatt hours. So that's one number that we see coming up over and over again in the code, and that is why we see that same number in the model law. The hazard mitigation analysis evaluates consequences of energy storage failure modes, and the approval of the analysis is contingent on demonstration that the consequences of the energy storage system failure, whether that be fire or gas, will be contained, controlled, or limited by system protections. So in addition to that large scale fire testing and the codes and the 9540 and all that other stuff, we have a hazard mitigation analysis that essentially will certify that this system can adequately respond to the worst that could happen within this system. That's essentially what hazard mitigation analysis is saying. It is required by the fire code. Large scale testing for systems over 600 kilowatt hours, that is, it is required. For large scale fire testing, again, that is UL 9540A test. Again, that only happens at 600 kilowatt, above 600 kilowatt hours. The testing results, as I said, will inform protections and requirement necessities, and the results from the test will demonstrate the fire will not spread to adjacent system areas, not that there will never be a fire. More fire code, fire remediation. So some folks may have heard that there is a reignition risk sometimes when energy storage systems catch fire. So what we have in New York State's code to deal with that is this fire remediation requirement whereby the storage developer is required to hire a team to come out in the event of a fire. So the local fire department is controlling the fire, they're putting it out, they're containing it. And then the energy storage developer is paying a team to monitor that site until there is no longer a risk of reignition. Because a lot of our fire departments are volunteer or otherwise, under-resourced. So we don't want to have them sitting, babysitting something that may or may not reignite. So we're going to put, in our fire code in New York State, we put that cost burden on the energy storage developer. That's what that is. Peer review. To hear me talk so much about how the 9540A test is a packet of results for your interpretation, I could understand if that sounds intimidating. I've been doing this type of work since before 2016, since before there was a UL 9540A test. I don't know 100% of what they're saying when I see them, and that's where the peer review requirement kicks in. You, as the authority having jurisdiction, have the authority to require the energy storage developer to pay for a third-party engineer, typically, or expert, otherwise as approved by the AHJ or authority having jurisdiction, to review those plans, to review the 9540A report, to review everything associated with this project, to make sure that everything is up to code and that everything is safe. So we really encourage folks, if you're not comfortable with interpreting a 9540A report, that's perfectly okay. You don't have to. You have the authority to require the energy storage developer to hire somebody to help you interpret that, somebody of your choosing. It's not like you get the resident engineer from Tesla coming in and telling you everything is safe for the Tesla project. That is not how this works. It is an independent third-party reviewer. So I really like to be sure the AHJs and fire marshals are aware of this because it can be really crucial in making sure that we have safe systems going online. Commissioning plan, also required by the fire code. It includes an operation and maintenance manual and a decommissioning plan. Decommissioning plan kicks in at the end of life or in the event of fire or other damage because, in case folks haven't put this together, a fire is the end of life of an energy storage system. Once these systems catch fire, there's nothing you can do, they're gone. And for that reason, also for incident response, there's no reason to put yourself in a dangerous situation to try to save this property. A lot of folks who train first responders on this technology will say, just let it burn and make sure that it doesn't propagate, make sure that the fire doesn't spread to other areas. And that is, as far as I can tell in my years of doing this, is sound advice. We've got some technology specific requirements here, back to the early table where we've got all these different types of electrochemical energy storage. I'm not going to go through all this, but these are just different things for different requirements for different technologies based on the normal charging and discharging operations. So you spill control and neutralization. During normal charging and discharging, lithium ion is not going to spill anything. So there is no requirement to neutralize spills. For lead acid, on the other hand, they are known to spill acid during normal charging and discharging operations. So we do have a spill control and neutralization requirement for lead acid. Folks who are interested in this is in chapter 1206 of the fire code. You can spend some time with it if you would like. We're coming up to the end here. I'm going to skip through a lot of these slides at the end because they all kind of say the same thing in a lot of cases. We've got again, this is the fire code. We've got 4 essential types of energy storage development. And we separate those into indoor and outdoor. We have 2 types of indoor installations. One is a dedicated use building. That is exactly what it sounds like. It is a building that's dedicated to the use of charging and discharging energy storage equipment. Nothing else happens in that building. A non-dedicated use building then is any other type of building. So if any other type of building has energy storage and anything else going on inside the building, then it's a non-dedicated use building. We also have two types of outdoor installations. Outdoor near exposures means there's basically anything combustible within 75 feet of the energy storage installation, or within 100 feet rather, of the energy storage installation. Outdoor remote means there is nothing combustible within 100 feet of the installation. So pretty simple. Dedicated use building is dedicated to the use of energy storage. Non-dedicated use building is a building that has energy storage in it and anything else going on. Outdoor near exposures is anything within 100 feet of the battery, and outdoor remote is nothing within 100 feet of the battery. We already went through the energy storage management system, and I want to have some time for questions. There's nothing really new here that I haven't said. Again, we've got dedicated use, non-dedicated, outdoor near exposure, outdoor remote. This is a look at what's inside a walk-in unit. So when you see those shipping containers out there, this is what's underneath the hood. We've got the battery racks, as we learned early in the presentation. We've got the fire suppression system here, fire extinguisher. We've got the energy management system. So that's the brain here. Where are we? This is the HVAC up here. This is a battery control panel. That's going to be accessible from the outside. And then we've got the inverters here, which are over with the energy management system. What the inverters do, for folks who don't know, is change DC or direct current to AC or alternating current. This is what energy storage cabinets look like. These again are about the size of a refrigerator, more or less. This is a cabinet system. Surprise, surprise, it's a bunch of cabinets right next to each other. Outdoor installations. So this is a good one because outdoor remote installations need to be 100 feet away from everything. Every energy storage system needs to be at least 10 feet away from everything. So you can't have an outdoor near exposure installation that has, say, a building within 10 feet or a lot line or anything else. That's essentially what this is saying. For outdoor installations, this is all the same information that was in the residential code. In fact, in the fire code, as it pertains to 1 and 2 family homes, it's almost verbatim what the residential code section says. So duplicative, but just want to highlight once again, individual unit separation and separation from doors, windows, and that sort of thing. Again, based on large scale fire testing. So we've got 3 feet unit separation and 5 feet doors, windows in the fire code. If the large scale fire testing, the 9548 report says that you don't need 3 feet or you don't need 5 feet, then you do not need that. That is how large scale fire testing works, and that is its purpose. As I said, you would find the email for my whole team at the end of the presentation, and here we are. Any one-on-one questions, technical assistance you may need, please feel free to email cleanenergyhelp@nyserda.ny.gov. That inbox goes to my entire team at once. We do kind of a collective democratic triage to see who on the team is best suited to handle each request. If it's not someone on the clean energy siting team, we will get it to the appropriate person at NYSERDA. You can also request technical assistance through a form on our site, which again is nyserda.ny.gov/siting. And you can find all of the guidebooks, including the energy storage guidebook, on the left pane of that website. Again, nyserda.ny.gov/siting. And I'm happy to take questions if folks want to use the Q&A or do through chat, or even if folks want to come off mute. We have 28, it looks like. So that might get challenging, but encourage questions. I see one right now. I will read it aloud and then answer. The question is, who is responsible for keeping the decommissioning costs current? Most municipalities can't keep up with this, and the owners are traditionally lax in doing this. Is this the peer reviewer? Will the owner pay for this after commissioning? So keeping the cost current is typically a 2% per year fee, or escalator, not a fee. It's an escalator is a better way to put it. So that is going to be built into your law. That approval of the project application is going to be contingent on the developer saying that they will pay that. It is on the developer to pay that. You do have a mechanism to get the developer to pay that if they don't pay that. If the developer is not paying that and there's no one at the municipality to notice that, that could be, a situation that just doesn't have a great ending, frankly. But it is part of a complete project application contingent for the approval of a project application that the developer agrees to pay that escalator year over year to keep the decommissioning cost current. The peer reviewer is a different thing completely. That is, again, help from an expert to review the application package that is funded by the project developer.
Bill, just let me elaborate on that.
Sure.
So decommissioning right now, as we see it on these things, is sort of this fixed concept, but the idea that will stay fixed and that the decommissioning plans that we're looking at now are going to be appropriate at the end of life is probably not realistic. I mean, we don't know we don't know the long-term effects of this. This is very new technology, even though lithium ion has been around for a while. The scale of the amount of material in there and the toxicity of it is really going to be, I think, something that's going to be changing. That's what I was asking about, not just an escalator for some inflation. I was thinking about an escalator for change in technology.
Well, you're evaluating a project. That project is not going to change in technology regardless of what happens to the technology in the market. The developer isn't going to be able to come in and replace that project that was approved with the newer technology, because they would need to submit a brand new application and go through the whole process over again, because they're essentially building a new project at that point. So what that third party, the decommissioning estimate is done by a third party engineer. So what that does is tell you, this with the specifics of this particular proposed system in mind. How are we going to decommission it? What is it going to cost? Those are things that we do know, right? Because we are at this phase in the development process, the developer is proposing a specific technology, a specific product that can be analyzed, that can, lend itself to, I don't want to say predicting the future, but just like reasonable expectations of what will happen and what will need to be done. Decommissioning plans might change as the technology changes. As a whole, the industry will, I hope, continue to evolve in what they put forward in their decommissioning plans. I hope that the recycling industry continues to improve, the energy storage industry continues to improve, but those are larger, kind of macro trends within the technology. Those aren't project by project trends or considerations even. And the decommissioning cost and approval is done on a project by project basis.
Are there any more questions for Bill? again, please either put them in the chat, or we're a small enough group that it'd be safe to unmute and ask it in verbally as well. I see there's just one from Leanne. Bill.
Sure. It says the question is, who will enforce the decommissioning? That's a great question. I usually say that during the presentation, and I am remembering that this time I didn't. The goal is that decommissioning fund is not used. The goal, the ideal scenario, what we want to happen is that the developer will decommission the system and restore the site on their own. The decommissioning security is there in the event that that does not happen. So if the developer is nowhere to be found, for one reason or another at the end of the term or at the end of the contracted period for that system, that's why you have the security. Then you have the money in your coffers to be able to dip into it and pay for the decommissioning of the project, rather than relying on them to still be around and do it themselves. So it's not really a question of enforcement because you're getting that money up front. There are things that are in the model law template that will trigger the decommissioning. Those would be kind of the entry points that, if there is, we'll say, a fire, and then the developer doesn't pay for whatever reason to decommission that system or replace it, that fire is going to trigger the decommissioning. So then you will be authorized to use that funding at that point. So it's less a method of, or it's less a question of enforcement and more a question of when are we authorized to dip into that money? What circumstances allow us to use the security versus under what circumstances do we need to wait for the developer to decommission the system on their own? Another question that says, if we have a local law enforcing the uniform and EDD codes requirements, do we need this additional law? Is there a benefit to having it in addition to the other? So as I said, you don't need a local law for the uniform codes. That's state law automatically without the need for local adoption. So everything I said about the fire code, everything I said about the residential code applies no matter what you do locally. So then the question becomes, what is the benefit of having a zoning law in addition to the uniform codes? That's a great question. It really, the main purpose is to ensure responsible development of those systems that are outdoor, the very large systems over 600 kilowatt hours. We want to ensure that that type of development does not encroach on the character of the community. And we want to be able to regulate that just like you would any other development. That said, I would argue that zoning for energy storage as a whole is probably much less necessary than it is for more impactful technology like solar. As I've said several times now, not just to this group. I say this like 10 times per presentation, so it gets funny to me after a while. But the energy storage systems really do require a small amount of space to hold a large amount of energy, versus solar, which requires a large amount of space to generate a modest amount of energy. So through a land use lens, the solar inherently has a much greater impact than the energy storage, but still a good idea to have zoning. Just to give the community some control over where this type of development is happening and how.
Any other questions for Bill? Last chance. Well, then I guess, Bill, unless you have anything else that you'd like to wrap up with.
No, just thank you, Nancy and Enka for hosting, and thanks everyone for spending some time with this material tonight. really appreciate your attendance and attention.
Well, thank you, Bill. And again, thank you, everybody, for also, thank you from me for attending tonight. I hope you found it helpful. We have one last session, which is next Monday, December 5th. And I'm going to put it in the chat right now. If you haven't registered yet, it's called Battery Energy Storage for First Responders. It is oriented for code officials, but I think you know, it might be useful for anybody who's looking at you know, battery energy storage coming into your community and wanting to be prepared for it. It does, you know, you might want to have your code official attend if you don't think they've already signed up, because this session, like I said, it's geared for code officials, but it also provides Department of State certification and, you know, for their continuing ed hours. And just a reminder that it will be a separate Zoom link for next Monday, different than tonight, and you'll receive the email like you have been ahead of time. Otherwise, again, thanks for coming out. I'll send out the webinar recording and Bill's slides in a couple days when it's all uploaded to where it has to go. And I wish you all a very good night and maybe see you next week. Thanks, everybody.